I'm very pleased to have the opportunity to share with everyone today. I'm John from MemVerge. MemVerge, it's a software company based in Silicon Valley, USA. We started 7 years ago. So our main research and development focus is on memory technology, which is why we are called MemVerge. 3 years ago, we brought this set of memory technology. We used a product from a cloud computing platform called Memory Machine Cloud, which is a highly efficient and reliable product. The core function of this advanced computing platform is to help users easily and efficiently run their tasks in the cloud environment, while also significantly saving costs and improving overall performance. Among our diverse user base, the majority are from the bioinformatics sector. Why is that? Because in the bioinformatics industry, there are a lot of computations, some of which are very large scale. So this falls under the traditional high performance computing category. However, many of these bioinformatics companies are not willing to invest in making their data centers very expensive and large. They don't have these resources, so they use the cloud to complete these computational tasks. So that's the situation here. We have 3 typical customers here. The first one, HPC, is the world's largest potato genome research company, and they are a Dutch company. The second one is an Australian company that focuses on cancer research. So in English, it's called oncology. And then MDI Bioscience is a very famous company in Maine, USA, with over 100 years of history in animal research. The research company, one of their projects is studying a special type of lizard that has a very strong regenerative ability. They hope that by analyzing the genes of this lizard, they can apply the findings to human medicine. So the customers we find in the bioinformatics industry are similar, whether it's animals or plants. For companies doing a lot of computing, well, today I want to share with you how we use Juice in these bioinformatics scenarios to improve performance and reduce costs for users. Now, in the bioinformatics industry, a very common, or rather the most popular workflow tool is called Nextflow. So what about this Nextflow? It is a Spanish company, but its largest user base is in the United States, followed by the United Kingdom, Germany, and Spain. Everyone might be quite familiar with workflow management tools, like a pipeline manager. It means that a complex computational workflow can be automatically managed. And then the architecture of Nextflow is like this. Nextflow has a control center head node, and this head node, it will read a copy of the definition file, then it will connect to a scheduler, and this scheduler controls where the actual computation happens. For example, if we are using the cloud, then there is a scheduler that needs to allocate cloud resources and interact with the head node of Nextflow, dispatching Nextflow tasks to different cloud resources, right? And then, to complete the execution of the entire pipeline, one of the most important and very crucial mechanisms in Nextflow is shared storage, because it essentially relies on this shared and centralized storage to track the execution status and progress of each task. It also uses the same shared storage to provide the sharing of data means that the output of certain tasks is the input for some downstream tasks. So this data interaction, the data interaction between tasks relies on this shared storage. And the third very important thing is a caching mechanism, because often those doing scientific research, for their projects, they will need to use public data resources. Public data resources are stored in a public, for example, SS3. If you access that SN every time you compute, it will be very slow. So Nextflow has a mechanism that allows using the shared storage provided by the scheduler to cache these external data. So actually all the logical mechanisms of Nextflow rely on this shared storage to function. So how do we very simply, essentially, basically, really actually incorporate with Nextflow? Well, it's like this. We wrote an open source plugin for Nextflow called NFFloat. Then this NFFloat essentially tells Nextflow that Memory Machine Cloud is a scheduler it can use and rely on. So Nextflow continues to work normally and efficiently, but all its task scheduling is sent through NFFloat to our Memory Machine Cloud Control Center called Upset. Upset will then interact with various cloud resources, for example, on Amazon Web Services or Alibaba Cloud, using cloud-native APIs to control the cloud resources. Basically, for each task, we will launch a new worker node, a new cloud instance, and then we will control and assign this task to the cloud instance. The execution of each task and the allocation of resources for each task. And then we have a feature, as I mentioned earlier, our main research is focused on memory. So Memory Machine Cloud has a feature that when it's us, we have the capability to take a snapshot checkpoint of a running task, and then we can move this snapshot to another cloud host, allowing the task to continue and complete on the other cloud host. Now, why do we do this? Well, there are a few reasons. The first one, which you might be more familiar with, is that in the cloud, besides the regular on-demand instances, there is something called spot instances, which are bidding instances. These bidding instances it is a very cheap option, possibly 80% lower than the regular price. However, it has a problem. The cloud can reclaim your spot instance at any time. If your task is not completed at that moment, you might have to start over from the beginning. This is very unfriendly for the bioinformatics industry. With our memory snapshot capability, we can move the task to another machine to complete it. In this way, all tasks and all pipelines can be completed using this instance, which can save a lot of costs. Okay, so as I just mentioned in Nextflow, the most important part is the shared storage. So we have done a lot of attempts and analysis on this shared storage, because this shared storage first needs to have relatively high performance, because if the entire pipeline implementation and execution rhythm is on this shared storage, then the overall performance of the shared storage needs to be good, and also essentially, so the caching I just mentioned, right? If the caching is very slow, it will make all the individual tasks very slow. If one task is slow, it will slow down the whole entire pipeline. So this is an extremely critical aspect. And of course, scalability is very important, because in various different pipelines, the amount of data varies, and different tasks use different amounts of data. So the capacity needs to be very flexible. Also, all these tasks basically use the POSIX file interface. Generally, these tasks are not programmed for other special types of storage, like object storage. Also, the people who write these programs usually don't. Biologists are scientists. They are not into computer science, so they tend to be simpler and directly use files to handle data. And of course, another very important aspect is the cost, which is crucial for these research institutions. And from the perspective of Memory Machine Cloud, this is one of our core values. This can significantly improve the performance to cost ratio. Therefore, the overall cost of storage is extremely important and incredibly crucial. Our initial first step was to start, when we initially tried, we used the Opt Center to set up an NFS server ourselves. The offender itself already had an NFS server. So at that time, we thought we would use the NFL server of Memory Machine Cloud itself to create this shared volume. As a result, we immediately discovered in these larger pipelines, the performance is indeed definitely very weak, because the NFS server becomes a single point of failure and a significant bottleneck. Another option is to use the NFS provided by the cloud. In Alibaba Cloud and in AWS, it's called EFS, or Elastic File System. The performance is okay, but the cost is very high. Additionally, the user has a lot of data, which is directly stored and processed in Amazon Web Services, AWS, specifically in S3. Therefore, using EFS is also very inconvenient because it requires a lot of copying. So later we tried S3FS, which can... The interface provided for this file is a POSIX interface, but its performance is very weak, especially with small files and many write operations. So I will have an analysis on this later. So there are also some users who have mentioned that in order to achieve high performance, they are willing to use FSX for Lustre, which is indeed a high-performance file system. However, the cost is very high, so very few users have the budget to run their pipelines on it. So in the end, we found that the best solution was to actually use this JuiceFS, and our architecture is basically... When Nextflow dispatches tasks, we use OpSender in order to efficiently and effectively and reliably to ensure optimal performance. In order to create a JuiceFS, we utilize the JuiceFS Community Edition to set up a JuiceFS metadata server. Then, the user provides a location for their object storage, and we can make this object storage location accessible to the Nextflow head node and all worker nodes. This setup meets the requirements and specifications of Nextflow, including all necessary information. So let me give you an example. For instance, there's a community for Nextflow, which is a group of people sharing common interests called... This is the most common Nextflow workflows shared with all the users in the Nextflow community. So in this NFC, the most common or most used one is called RMCQ, which is RNA sequencing. You know, this is very popular. This is a relatively complex pipeline, which is in total with a total of approximately 276 tasks in the pipeline. The basic steps start with carrying out quality control on the data set obtained from the sequencer, which involves a process of cleaning out some irrelevant data. Then it performs a step called alignment. Alignment, which means taking this data collected from various physical samples, such as different types of samples, and then analyze the results to draw conclusions. Using the existing reference data to make a comparison and determine what kind of gene or RNA it is. And after that, he needs to do some additional necessary and important organizing and trimming so that he can proceed to the next step to generate the report. Yes, this is a relatively complex and it will run for a long time, an extensive and detailed pipeline. So let's compare the results of various runs. The first column here is the method used. The second column is CPU time, which is the CPU. And the third column is wall time, which is the actual time spent. CPU time is core hours, meaning if you continue running for an hour, it's 4 core hours. 4 brackets, and then the last column is our cost. So in the first step, we used the cloud's EFS and then integrated it with Memory Machine Cloud. And as you can see, it took 7 hours to run the entire pipeline, but the same pipeline took 26 hours to run with CIFS because it took so long. Its cost, even though it used SM, was very high. EFS, of course, is very expensive. And then we have a company, it's called Sakara. It's the commercial version of Nextflow, the company that produces the commercial version of Nextflow. He specifically developed a unique file system called FusionFS for the Nextflow project. FusionFS runs seamlessly in conjunction with AWS Batch, and it successfully ran for 7 hours. It took about 45 minutes, okay? And then the cost of the cloud resources was $90, and Fusion itself also has some license fees, okay? When we ran it with JuiceFS and Memory Machine Cloud, our best run was completed in 6 hours and 56 minutes, and our cost was only $20, so it was much cheaper than FusionFS. So this is the result we achieved, and we shared it with all our users, and they are quite satisfied. Now, let's take a closer look. This is a specific comparison with S3FS. So You see, actually, we just look at the wartime. It runs for 27 hours. This is one instance. And compared to our JuiceFS, we have 7 hours and 6 hours, 56 minutes, these two JuiceFS instances. These two are the differences between using on-demand instances and spot instances with Memory Machine Cloud. Why use spot instances? Faster, because when we use spot instances, Memory Machine Cloud will actually look for the same price, but better machine types. So that's basically what it means. The spot instance actually uses a newer and more advanced Intel model to run, so its processing speed is significantly faster. However, regardless of whether we use on-demand instances or spot instances, we have a very significant advantage over CIFS. When I was discussing this detailed presentation with Juice Data, I specifically asked a colleague of mine to run it again. This RNA-seq card, because its dataset is different, it means that each time the result will be a little different. You can see this result because it has over 200 tasks. So this graph is very faint, but each line actually represents a task. The longer lines mean it took more time, and you can see that many tasks are in progress. And then there are also many tasks that have dependencies because the subsequent tasks definitely need to be completed after the preceding tasks are finished. So we used JuiceFS to run for 9 hours. This time it took 9 hours and cost $23. Okay. With the same setup, we used CIFS to run, and the result was that after running for 9 hours, the pipeline failed. And by that time, the cost had already reached $1.37. Why? Because some tasks, you see these very long red lines, failed, meaning they ran for a long time before failing. Because it took too long, Nextdoor gave up. Then Nextflow tried a few times and said that this pipeline couldn't be completed, so they gave up. So I looked deeper to see why these long red lines were happening. Then I discovered that this task was actually a sort task, and you can see its I/O pattern is like this. It needs to write a lot of small tasks, basically. Small files, and each file is under 500 bytes because he writes such small files to S3FS. It makes it very slow, and on average, we can complete writing one file every 2 minutes, even though it's very small. So that's that. The small file size significantly impacts the performance because each write operation involves overhead. This overhead includes establishing a connection, sending metadata, and confirming the write, which takes time. Despite the small size, these operations are time-consuming, leading to an overall slow process. So the newcomer was really not good, and this job, after running for about 7 hours, he gave up. Nextflow has a timeout, meaning that if your task runs too slowly, it will time out. Similarly, when we were facing this, we saw that on average, we could complete 2.5 files per minute, and its throughput, actually the I/O was much faster, but the throughput was about the same because the file was actually a very small file. Right, so this is one of the core advantages of range isolation-free zones, and range isolation-free zones and free cores is that they can help us handle a large number of small files. Yeah, all right then. We will also do some other things like perhaps improvement. First of all, there are many users whose original data sets are stored in object storage, such as, for example, already known in S3. But if we define our shared storage in Nextflow as a POSIX interface, then Nextflow will automatically copy the data from S3 to our staging area, our shared storage, which we call staging. The staging process is very slow, but it's actually unnecessary because Joseph is also on S3, so it can actually be avoided. So we will use the Juice S3 interface to provide a solution. To provide an S3 interface for the Nextflow system, this can effectively avoid the preliminary step of the data staging process. Moreover, there currently exists a cache group, which is essentially a cloud-based service. We are also currently exploring this cloud service in greater detail. Recently, one of our users had a Nextflow pipeline where he This Nextflow pipeline will simultaneously issue approximately 200 tasks, so you have around 200 nodes. However, they will all share the same set of reference data. So if there are about 200 nodes, it might require staging and caching on each individual node, which can be quite challenging indeed. It's quite inefficient. So if we use this cache group, we hope to avoid each node doing its own caching. And then also when we are now mounting this JuiceFS, I think it's still quite a rough approach would be to use the default parameters for almost all settings. However, for each task's specific attributes, especially the tasks we have run before, I think we can further optimize these parameters to improve the performance of each task. Okay, I will stop sharing here.